Hello everyone, this is Dr. Habib Ahmed. I welcome you back to my channel. In today's video, I'm going to demonstrate the simulation of tandem solar cells using SCAPS 1D software, focusing on an advanced structure with an indium gallium phosphide top cell and a gallium arsenide based bottom cell. I will walk you through every step of the process from setting up the device layers to configuring the materials, doping concentrations, and other critical parameters. You will learn how to model the key components such as the window layers, the emitter and base layers, and the base surface field to accurately simulate the performance of this high efficiency tandem solar cell. Whether you're a student working on a project, a researcher exploring new solar technologies, or just curious about how tandem solar cells work, this tutorial is tailored to help you gain practical insights and hands-on experience with SCAPS 1D software. So get ready to enhance your simulation skills and deepen your understanding of tandem solar cell technology. Let's jump in right into SCAPS 1D software. But before that, let me tell you a brief background about tandem solar cells and how this structure is going to work. Tandem solar cells are designed with multiple stacked semiconductor layers, each optimized for its layer thickness, doping concentration, its content, and energy band diagram to capture different wavelengths of light. This layered structure approach significantly increases efficiency as compared to the traditional single junction solar cells. A common example, for example, is the dual junction solar cells which features two layers. The top layer, which is based on indium gallium phosphide, captures shorter wavelengths, for example, blue and green light. It often uses material, for example, in this case I'm using indium gallium phosphide, while the bottom layers captures longer wavelengths, for example red and infrared light, typically using other materials, for example silicon, germanium, but in this case I'm going to use gallium arsenide because gallium arsenide has a narrower band gap. In this case I kept the band gap of the indium gallium phosphide to approximately 1.875 electron volts, and the band gap of the gallium arsenide layer to which is approximately 1.44 electron volts. So this structure allows the cell to convert a broader range of sunlight into electricity, maximizing energy conversion. Now let me talk a little bit about the key components of this tandem solar cell. One of the key components is the emitter and the base layers. But before that, let's talk about the window layer. So a window layer is a transparent conductive layer that allows sunlight to pass through it with minimal absorption, ensuring maximum light reaches the active layer, where the active layers are the emitter and base layers. In this case, for the top cell, the emitter and base layers are based on indium gallium phosphide, and for the bottom cell, the emitter and base layers are based on gallium arsenide. So because of its transparent conductive property, it allows sunlight to pass through it with minimal absorption, ensuring maximum light to reach the active layer. This window layer also serves as an electrical contact to complete the circuit. The other key components are the emitter and base layers, which are also called the active layers. These layers work together to generate and collect charge carriers, which are electrons and holes. The emitter located at the top is thin and heavily doped to create a high concentration of charge carriers. The base under the emitter is thicker and it absorbs most of the light where charge carriers are generated. Now in tandem solar cell we also have a base surface field layer positioned at the cell's backside. The base surface field layer reduces recombination losses by creating an electric field that repels minority carriers, enhancing the overall efficiency of the solar cell. Now, in a tandem solar cell, one of the key components is the tunnel junction. You have to connect the top and the bottom cell. They are in a series connection. And in order to facilitate this series connection, we need a tunnel junction. This is a crucial component which connects the different layers in series, enabling charge carriers to move between the layers while maintaining the necessary voltage for efficient energy conversion. The tunnel junction's properties are carefully engineered to match the adjacent layers' band gaps, minimizing losses and ensuring optimal performance of the solar cell. Together, these components allow multiple multi-junction solar cells to capture and convert a broader spectrum of sunlight into electricity, achieving much higher efficiency than traditional solar cells. So that was a brief introduction into tandem solar cells and the different layers of tandem solar cells. Now let us talk about the business, which is simulation of a double junction solar cell. So before performing the simulation on SCAPS 1D, I want to show you how I performed the simulation of the tandem solar cell previously using Silvaco TCAD software. Silvaco TCAD is a more comprehensive tool. It gives you better results, accurate results. You may want to double check your results with SCAPS 1D as well. But if Silvaco TCAD is available, it's a better option, and always I would trust more the results of Silvaco TCAD as compared to the results of SCAPS 1D, because we have got a lot of limitations in SCAPS 1D software. So if you are interested in the simulation of tandem solar cells using Silvaco TCAD software, I've already posted a video on this on my YouTube channel, so you can always visit my YouTube channel in order to learn about the simulation of tandem solar cell using Silvaco TCAD software. And I can briefly show you some results from my Silvaco TCAD simulation of tandem solar cells. Here is the code. I'm just going to run through the code. And then here is the layer structure diagram, meshing, the doping concentration in different layers. Here are the doping profiles. The energy band, the energy levels of different layers inside the structure. Similarly, here is the energy band diagram under thermal equilibrium. The photon generation rates throughout the structure, photon absorption rate, energy band diagram of the structure under light conditions, the IV characteristics of the solar cell, the power curve for the solar cell, and then the spectral response and the internal and external quantum efficiency of the solar cell. And then here are the final performance parameters. So it gave me a short circuit current density of 13.25 approximately milliamps per centimeter square, an open circuit voltage of approximately 1.74 volts, fill factor of 86.6%, and an efficiency of 19.92%. Ignore this negative sign because it's just about how you use the formulas. We can always make it positive. So the purpose was to show you that I have already performed the simulation in using Silvaco TCAD, and today I'm going to demonstrate how to perform the simulation of a double junction solar cell using SCAPS 1D software. Before proceeding with the simulation, I want to show you that I'm going to perform the simulation using the latest version of SCAPS 1D, which is SCAPS 3.3.11. And the question is, how do you get the latest version of SCAPS 1D software? So in order to get the latest version of SCAPS 1D software, what you need to do is you can always send a request to Mark Bergelman, and pardon me if I'm mispronouncing the name, but Mark is a really amazing person. I requested him last weekend to send me the latest version of SCAPS, which is 3.3.11, and he was really responsive and super nice and sent me the latest version of SCAPS 1D software. So you can also send an email to Mark to receive the latest version of SCAPS 1D software. I'm really thankful to Mark for providing me the latest version of SCAPS 1D software. So now let me tell you about the plan. So generally what we do when we perform the simulation of a solar cell under light conditions, we switch this option to light conditions, and then we mostly perform the simulation at AM 1.5 G condition, and then I go for IV characteristics in the range of depending on the open circuit voltage. For example, in this case we are expecting an open circuit voltage close to 2.7 2.8 volts, and then I would stop the simulation after we arrive at the open circuit voltage. I also look at the quantum efficiency aspect of the solar cell and define a range for the wavelength of the solar cell, and then I go to set problem, and here I define different number of layers. So SCAPS gives you an option to include up to 7 number of layers: 1 2 3 4 5 6 7. Now if you look at this structure, for which I've already performed the simulation in Silvaco TCAD, you may observe that I've got in total of 11 number of layers. So first, I've got more number of layers than SCAPS 1D can accommodate, and secondly, SCAPS 1D cannot perform the simulation of tandem solar cells anyway. It gives you convergence errors, and you cannot perform it anyway. So then how do we perform the simulation? Is there any alternative for this? Yes, there is. So you cannot really directly build the structure, but the way it works is you can actually write a script in SCAPS 1D, and in this script first you construct the top solar cell and save the structure, and then you construct the bottom solar cell and save the structure, and you combine the two structures in a script, and I'm going to show you how to write the script in order to perform the simulation of the tandem solar cell. So effectively the SCAPS script is used to simulate and calculate the IV characteristics for a series connection of two solar cells, whereas SCAPS is a tool used for modeling the electrical characteristics of thin film solar cells. So what we are going to do is, first I'm going to construct, let's go back to our structure. So first I'm going to construct the top solar cell running from layer number 1 to layer number 4, and then secondly I'm going to construct the cell number 2 running from layer number 7 to layer number 11, and I tried to include the tunnel junction layers, and I combined it with the second cell but it does not work with the tunnel junction. So you can assume that SCAPS automatically creates the tunnel junction, or it just combines the result of the two solar cells which are in series. So once again, I'm going to construct the indium gallium phosphide based top solar cell running from layer number 1 to layer number 4, from the window layer to this base surface field, and I'm going to save the structure. Then later I'm going to construct the bottom solar cell based on gallium arsenide running from layer number 7 to layer number 11, once again running from the window layer to the base surface field. And then finally I will combine the two structures in the SCAPS 1D script, and we will perform the simulation. So this is kind of an extensive process. So let us go ahead and create the structure for the top solar cell. Okay. And I'm going to, okay, so let me restart SCAPS 1D software. I want to full screen it. Cool. I want to perform the simulation under light conditions. I want to run the IV for the top solar cell. I got a band gap of approximately 2 electron volts, and to be more exact, for the indium gallium phosphide, my band gap is 1.875 electron volts. So I'm going to run the simulation from 0 to 2 volts for the top solar cell, which is based on indium gallium phosphide. And for the quantum efficiency, we will run it from 100 to 900 should be enough. Then we set up the problem and create each layer one by one. Let us go back, making sure that we are performing the simulation under light conditions. So light, M1.5, IV is running from 0 to 2, stop after VOC, quantum efficiency running from for wavelengths in the range of 100 to 900 nanometers. Let us set up the problem. Cool. So we click on add layer to create the first layer, which is indium aluminum gallium phosphide. Its thickness is 30 nanometers. So from the menu we are going to select thickness, and it's going to be 30 nanometers. We hit enter. Also, as far as the band gap is concerned, already from Silvaco TCAD simulations, I figured out its band gap, and its band gap is 2.33 electron volts. Similarly, its electron affinity is 4.2 electron volts. Its dielectric constant is 10.5. Its effective density of states in the conduction band and valence band are 3 10 to the power of 18 and 2 10 to the power of 19. Its electron and hole thermal velocities are 4 10 to the power of 6 and 2 10 to the power of 6. Similarly, I assume that its electron mobility is 4000 and its hole mobility is 200 centimeters square per volt second. Similarly, from this structure, we can see that we have got a whole concentration of 2 into 10 to the power of 18 per centimeter cube. So assume an electron concentration of 0 and a whole concentration of 2 10 to the power of 18 per centimeter cube. So, and then we can add a defect as well. 1 into 10 to the power of 14 per centimeter cube should be good enough. So click on add. Let me double check the parameters. Indium aluminum gallium phosphide, a thickness of 30 nanometers, band gap of 2.33, 4.2, 10.5, 3E18, 2E19, 4E6, 2E6, 4200, 0, and its whole concentration is 2 10 to the power of 18 per centimeter cube. Cool. Now we need to add an absorption file to the indium aluminum gallium phosphide. It gives us more accurate results if you add an absorption file. And for the absorption file, I'm gonna choose indium gallium phosphide, and we click on add. So the first layer is added, and now let me show you. So we go to C, program files, SCAPS 3311, absorption, and I go to the indium gallium phosphide file. Now, this file is not already available in the absorption folder of SCAPS 1D software. We got a lot of other absorption files, but not the one for indium gallium phosphide. So I created it myself. We got 2 columns. The first column corresponds to wavelength in nanometers from 300 to 700 nanometers, and the second column corresponds to alpha, which is the absorption coefficient, corresponding to the wavelengths in the range of 300 to 700 nanometers. Where did I create this from? So I actually now let us go back to the results. So I actually found it in literature. Here is a figure, absorption coefficient plotted versus wavelength in the range of 300 to 900 nanometers, and the red curve corresponds to the absorption coefficient of indium gallium phosphide with 50% indium and 50% gallium. So I looked at the values of the absorption coefficient at 300, 350, 400, 450, 500, and so on. And I created this absorption file, and then I saved it inside the absorption folder of SCAPS 1D software, as you can see over here. Later, we are also going to need the absorption file for gallium arsenide. Which is over here, and the absorption file for gallium arsenide is already available in the SCAPS absorption folder, so I do not really need to create it. But if you want to work on indium gallium phosphide, you got to create the absorption file for gallium phosphide. So here is the SCAPS 1D software, and you go to the absorption folder, and you need to save the absorption files inside this absorption folder. Okay, so now we need to create the second layer, which is indium gallium phosphide, and its thickness is 50 nanometers, and its doping concentration is 2 into 10 to the power of 18 per centimeter cube, in its p-type. So we click on add layer, and we call it indium gallium phosphide. Its thickness in nanometers is 50. Similarly, the band gap of indium gallium phosphide is for 50% indium, 50% gallium is 1.875, and I already determined it from the simulations of Silvaco TCAD. Similarly, its electron affinity is 4.2. Its dielectric constant is 10.5. Its density of states in the conduction band is 3 10 to the power of 18. Density of states in the valence band is 2 10 to the power of 19. Its electron thermal velocity is 4 10 to the power of 6, and hole thermal velocity is 2 10 to the power of 6. Similarly, its electron mobility is 4000, and its hole mobility is 200 centimeters square per volt second. And I've set its hole concentration to 2 into 10 to the power of 18 per centimeter cube. So I'm setting the electron concentration to 0, the hole concentration to 2, 10 to the power of 18 per centimeter cube. I'm going to add a defect to it as well. Click on add, and then we select the absorption file for indium gallium phosphide, which I already created and saved it inside the absorption folder of SCAPS software. So choose it. Let me double check the parameters. Everything looks good, so we click on add. Now we add the third layer, which is 550 nanometers indium gallium phosphide, and it has got an electron concentration of 7 10 to the power 17 per centimeter cube. So instead of clicking on add layer and entering all the properties once again, we got another option as well. We got the same indium gallium phosphide material. We just need to change its thickness and its doping type and concentration. So what I do is I right click on indium gallium phosphide and then click on duplicate layer, and then click on this layer, like left click on this layer. This is my layer number 3. Its thickness is 550 nanometers, and its doping concentration is N-type, and it has a doping level of 7 into 10 to the power of 17 per centimeter cube. Exactly. So let me double check the parameters. Click on accept. And now the final layer over here is indium aluminum gallium phosphide, and it has got an electron concentration of 2 10 to the power of 18 per centimeter cube, and its thickness is 30 nanometers. So some of the properties of indium gallium nitride phosphide is the same as indium aluminum gallium phosphide, so I'm going to copy that layer once again. Click on it. I'm gonna rename it to indium aluminum gallium phosphide. Set its thickness to 30 nanometers. Set its band gap to 2.33 electron volts. These parameters are the same, and then it's so let me check. Is it electron concentration? Yeah, electron concentration of 2 10 to the power of 18 per centimeter cube. 2 10 to the power of 18 per centimeter cube. And the absorption file is already selected, as you can see over here. In the path for the file is given. So now you know that I've chosen the absorption file for indium gallium phosphide for this indium aluminum gallium phosphide layer. Double check all the parameters. Sounds good. So click on accept. Okay. And now we can save the structure. So click on save, and we gotta save it inside the SCAPS 3311 DEF folder. definition of the structures folder, and I'm going to rename it to InGaP de. We can name it InGaP tops. No, InGaP should be enough. .def. Click on save. We can save it to like the folder that we created for this video tutorial, so we can save it over there as well. DEF. Click on save. Cool. Now we click on OK, and the problem is already set up, so click on OK and then click on calculate single shot. So now it's running the simulation. The voltage is ramping up. Now it's performing the simulation for the quantum efficiency, going up at 180, 190, 200, still going. Simulation is finished. We click on IV. Here is the IV characteristics for the solar cell, and we can also see the efficiency and other parameters. So what I'm gonna do is I'm gonna open a Microsoft PowerPoint file. Blank presentation, and let me call it top cell. Similarly, Control C. Let us create another page for the bottom cell. Results, bottom cell. Control C. Cool. And using the snipping tool, I'm gonna take a snapshot of the results. Okay, it did not cover all the results, so I'm gonna do it once again. Cool, and copy and paste it over here. Similarly, we also want to look at the quantum. So the efficiency of this top solar cell is 23.45, fill factor of 91.3, JSC of 15.72, VOC of 1.634 volts. We can also look at the quantum efficiency, but I'm more interested in like the basic performance parameters, so let's forget about the quantum efficiency. Now we already simulated the top part of the tandem solar cell, which is indium gallium phosphide based top cell. So you go to actions, clear all simulations, and we can set up the problem. Instead of messing up with the previous structure, it's better to close the program and restart another SCAPS 1D. window. Okay, full screen it, click on light conditions, IV running, and this bottom cell is based on gallium arsenide. So a voltage range from 0 to 1.5 volts should be enough. Similarly, quantum efficiency running from 300 to, I would say, 1500 nanometers. And cool. Now we got to set up the problem. So let us visit the structure once again. The bottom part of the structure starts from the indium gallium phosphide window layer. Okay, and we already defined the properties for indium gallium phosphide, so a better way to do is to load the previous structure, indium gallium phosphide, load. Okay, delete the layers which are not required. Right click on this layer as well, remove layer, and let's go to the structure once again. So this layer is 40 nanometers indium gallium phosphide, and it has a whole concentration of 3 × 10^18. So click on this, set the thickness to nanometers. Thickness is 40 nanometers, and it has got a whole concentration of 3 × 10^18 per centimeter cube. Do we need any more information from here? No. That much information should be enough. 40 nanometers, 3 × 10^18 indium gallium phosphide. 40 nanometers indium gallium phosphide with a whole concentration of 3 × 10^18 per centimeter cube. Now we got to introduce a 500 nanometers gallium arsenide layer. So accept this one, click on add layer. This is gallium arsenide, or you can also call it, this one is P type, so you can also call it P gallium arsenide. Its thickness is 500 nanometers. Hit enter. It's and we gotta set up some more properties for this. In fact, we can enter the carrier concentration for this layer. Thickness of 500 nanometers and a whole concentration of 2 × 10^18. So set the electron concentration to 0. Set the whole concentration to 2 × 10^18 per centimeter cube. And now we have to set up the rest of the properties for this layer as well. So its band gap is 1.42. Similarly, its electron affinity is 4.1. Its dielectric permittivity is 12.9. Density of states in the conduction band is 5 × 10^17. Density of states in the valence band is 7 10^18. Electron thermal velocity is 1 × 10^7 centimeter per second, and whole thermal velocity is 3 × 10^6. Similarly, its electron mobility is 8500, and its whole mobility is 400 centimeter square per volt second. Let us double check the parameters. 500 nanometers gallium arsenide. Okay, 500 nanometers hole concentration. Add a defect. Click on add and set its absorption file. Its absorption file is already available in SCAPS 1D software, so click on gallium arsenide and click on select. So this layer is all set up. Click on add and that would be it. Now we need to add the next layer, which is 2 micrometers gallium arsenide with an electron concentration of 7 into 10 to the power of 16 per centimeter cube. So instead of defining all the properties, what we can do is we can duplicate the top p-type gallium arsenide layer, right click on this layer and click on duplicate layer. So now this layer is gonna be n-type. Its thickness in nanometers is 2000. Let me double check. 2 micrometers, yes. And it has got an electron concentration of 7 10 to the power of 16. So set the whole concentration to 0 and set the electron concentration to 7 into 10 to the power of 16 per centimeter cube. The absorption file is already chosen for this layer, as you can see from this path, and the defect is already added as well. So click on accept. The next layer is 100 nanometers aluminum gallium arsenide layer. And let me check if I already created an absorption file for aluminum gallium arsenide. In fact, I looked for it and I found that it's kind of close to the absorption file of absorption properties of gallium arsenide. So we are going to select the absorption file of gallium arsenide for the aluminum gallium arsenide layer. Talking about the properties of the aluminum gallium arsenide layer. So click on add layer. Layer number 4 is aluminum gallium arsenide. Its thickness is 100 nanometers. Its band gap is 2 electron volts, which I found from the Silvaco TCAD simulations. Dielectric constant of 3.9. Electron affinity of 3.9, dielectric constant of 11, density of states in the conduction band of 4 10 to the power of 18, density of states in the valence band of 2 10 to the power of 19, electron thermal velocity of 1 10 to the power of 7, hole thermal velocity of 3 10 to the power of 6, electron mobility of 4000, hole mobility of 200, and its electron concentration is 5 10 to the power of 18. And we are gonna set its hole concentration to 0. Similarly, we add a defect to it as well. Click on add. Click on absorption, set absorption file. And we are gonna choose the absorption file of gallium arsenide for this layer as well. So let me double check this layer. 100 nanometers, 5 10 to the power of 18 n type. 100 nanometers, 5 10 to the power of 18 n type. Click on add. Similarly, now the final layer is 200 nanometers gallium arsenide N-type. So click on add N-type gallium arsenide, 200 nanometers. Set the rest of the properties as well. Add a defect, click on add. Let me double check the properties. 200 nanometers N is equal to 1 10 to the power of 18. So click on add. Now we added 1, 2, 3, 4, 5 layers. From 7 to 11 we got 5 layers. This structure is also completed, so we can save it over here as gallium arsenide.def inside the DEF folder of SCAPS 1D software. Similarly, I'm also going to save it in another folder at desktop. Click on OK. Set up the problem, OK. And now click on calculate single shot. Still running. So it gave some convergence error for the quantum efficiency part, but the IV part is already done, and we are more interested in the IV part. It gave me a VOC of 1.14, a JSC of 12, fill factor of 83, and an efficiency of approximately 11.5%. So let me save these results as well. Click on action, and I'm gonna close SCAPS 1D now. It's always good to double check on the SCAPS 1D structures file, which is DEF file, if you have already saved the results. So I I see like the previously saved files, but not the currently saved indium gallium phosphide and gallium arsenide top and bottom cell files. But I've already saved them in another folder. So we got this one and we got this one. So we are going to copy them and paste them inside the definition folder, DEF folder of SCAPS 3311, which is the latest version of SCAPS software. So now we got the top cell and the bottom cell structure files, and we need these two files in order to run the simulation of double junction solar cell. So we open the SCAPS software once again. So as I already told you that we cannot directly run the simulation of multi-junction, or you can also call it tandem solar cell, by going to set problem and creating the structure. We have to run it, we have to create the individual top and bottom cells, and then we have to run them inside the script setup. So we go to script setup, and here the SCAPS script is used to simulate and calculate the current voltage characteristic curves for a series connection of two solar cells. So now we are going to write the script for the simulation of the tandem solar cell. So we start with the commands of clear all and clear actions. Clear all and clear actions is used to clear any previous data or actions from the memory. And then we write action light. It simulates light exposure on the cells, indicating that this simulation involves illuminated conditions. After this, we enter the command of iv.start v0 action iv.start v space 0. This command sets the starting voltage for the IV characteristic curves simulation at 0 volts. Action iv.stop v3. This command sets the stopping voltage for the IV curve simulation at 3 volts. So we have created a tandem cell with an open circuit voltage of the, so here we can see the open circuit voltage of the top and bottom cell. For the top cell we got an open circuit voltage of 1.63. For the bottom we got 1.15. So I'm expecting the open circuit voltage of the tandem cell to be around 2.8. So that's why I've set the stop voltage to 3. I want to run the simulation up to 3 volts. If you set a really small value, you might face convergence issues. Action iv.increment 0.02 sets the voltage increment step at 0.02 volts. Action iv.check action ensures all actions are correct and ready for simulation. Action iv.stop after VOC means that the simulation will stop after reaching the open circuit voltage. So after this we will simulate the top cell. This is the backspaces are actually used to include a comment. So you load the definition file for the top cell, and I have named it indium gallium phosphide. So you this command loads the device structure and material parameters for the top indium gallium phosphide cell. Similarly, calculate single shot runs a single simulation to calculate the IV characteristics of this cell. Get IV ZU stores the IV curve data for the first cell in the variable ZU. Similarly, we enter the commands for the bottom cell, which is cell number 2. Load definition file gallium arsenide.edef loads the device structure and material parameters for the second cell, which is gallium arsenide based bottom cell. Calculate single shot runs a single simulation to calculate the IV characteristics of this cell. Get IV VW stores the IV characteristic curves data for the second cell in the variable VW. Now we want to calculate the series connection IV characteristic curves. For that purpose, we enter the command math series XY ZU VW space NZ. It actually combines the IV curves of the two cells in series, and it stores the results in this variable. Then we want to visualize the results. So plot draw ZU actually plots the IV curve for the first cell. Similarly, plot draw VW plots the IV curves for the second cell. Similarly, plot draw XY plots the IV curve of the series connection of the two cells. Now we want to extract the solar cell characteristics. Math characteristics.all CXY computes and stores all relevant solar cell parameters in the variable CXY. Similarly, math characteristics dot VOC XXY extracts and stores the open circuit voltage in this variable. Similarly, math characteristics dot JSCYXY extracts and stores the short circuit current density and the variable, which is given over here. Similarly, math characteristics dot FF ZXY extracts and stores the fill factor information in this variable. Similarly, math characteristics dot VMPPWXY extracts and stores the current density, extracts and stores the voltage at maximum power point in the variable VXY. VXY. Similarly, math characteristics dot JMPP WXY extracts and stores the current density at maximum power point in this variable. And finally, we show the script variables. It displays the values of the script variables after the simulation has been completed. So overall, this script simulates the IV curves for two different solar cells connected in series. It visualizes the results and extracts the key performance parameters of the series connected solar cells. We can save it as well. You can call it, for example, double junction solar cell dot script and click on save. Click on OK, click on execute script, and just pray that we did not make any error in the script file. Okay, let us now analyze the results. Let me go to the script file. We don't see it over here, but I already saved it in another file, another form. Click on OK. Okay. So let's go to this window now, and let us analyze each and every one. So for example, if you look at this script file, we see the VOC information in the X variable. So this variable gives us the open circuit voltage information. So my open circuit voltage for the tandem solar cell is 2.776, or you can say it's approximately 2.78 volts. Similarly, The Y variable gives me the short circuit current density, this variable over here. So my short circuit current density is approximately 12.32 centimeters square, milliamps per centimeter square. Similarly, the Z variable gives me the fill factor. My fill factor is approximately 90%. The U variable gives me the efficiency. This variable gives me the, where is the, we got the VWXY, where is the U variable? So there might be some problem with the script, or I might not have included the command for the efficiency. 1 2 3. Okay, let me double check the script file. Continue, action, script setup, fill factor. So VOC JSC fill factor. I did not include a command for the efficiency. So I'm going to do that. Math characteristics dot eta uxy, and then click on save, yes, click on OK, execute the script once again. Okay, now I got the U variable as well. So the U variable gives me efficiency. Here is my U variable. My efficiency is approximately 30.83%. Similarly, the V variable gives me the voltage at the maximum power point, and W gives me current density at the maximum power point. So VW gives me the voltage at the maximum power point, and W gives me the current density at the maximum power point. We can also click on these options, save script variables, to save the results in an Excel sheet. Similarly, what we can do is we can also plot these results in, for example, origin. So I need 6 columns, 2 each for the top cell, the bottom cell, and the tandem cell. One for voltage and second for current density. So I click on the right column, and then I press Ctrl plus D, click on yes, and I need 4 more columns. So click on OK. Then I come over here and find the corresponding. So I got 58 values in this one and 58 values in this one. So I'm gonna copy this one first, like the entire data in this tab. Press Ctrl plus C, and then come over here to origin, press Ctrl plus V. We don't need the serial numbers, and then Ctrl X and paste it in the first column. This is the voltage column. For the current column, copy all the data, Ctrl C, come over here to origin, Ctrl V. We don't need the serial numbers once again, Ctrl X, and paste it into this column. Okay. Similarly, we've got how many entries? 82 number of entries in that column. This is the voltage for the bottom cell. Or maybe the top cell. We are going to figure it out. So Control V, delete these numbers. Control V. I'm going to label it as X, or independent variable. Similarly, we got 82 entries over here. Similarly, we got 82 entries in this tab, so they do match with each other. Copy the entire data in this tab as well. Control plus C. Come over here. Control plus V. Delete the series numbers. What happened? Okay. Click on it once again. Delete. Click Control X. Control V. Okay. And finally, the series voltage and the series current density. Control plus C. Control plus V. Cut this data from here and paste it over there. I'm also going to assign this column as independent variable, since this is the voltage column. Similarly, copy the data for the series current density. Control C, Control V. Delete these numbers. Control X, Control plus V. You can call this the voltage column. Its unit is going to be volts. Similarly, you can call this the short circuit current density column, and its unit is milliamps per cm square. Cool. And now we plot all these columns. So here are the results in origin. JSC, voltage, etc. The scales in fact show the top axis, the left one, the right one. Click on OK. So you see all these axes now. Similarly, we can increase the thickness of these curves. They are dependent on each other. So we go to line, we go to thickness, set it to 4, hit apply, click on OK. And similarly, I don't need the scale above 0, so I'm gonna set the scale to from minus 17.5 to like 0. Hit apply, click OK. The red curve corresponds to the top cell. This gray curve corresponds to the bottom cell. And the blue curve corresponds to the tandem cell. So move it over here to the left, and then you can play around with this figure further as well. Let me full screen it. Anyhow, so you see the results. Similarly, in SCAPS 1D, we can click on continue. And to see all the results here, we click on these two current densities as well and hit refresh. So now you see all these characteristic curves, and in order to redefine the scale, we switch the scale from auto to manual and set y maximum to 0. Hit OK. So now you can see the characteristic curves as well. So here are all the results, and that's how you perform the simulation of the tandem solar cells in SCAPS 1D software. That's it for the simulation of tandem solar cells using SCAPS 1D. We have explored how to set up and analyze an indium gallium phosphide top cell paired with a gallium arsenide bottom cell, and seen how these layers work together to enhance efficiency. If you found this video helpful, don't forget to give it a thumbs up and subscribe for more in-depth tutorials on solar cell simulations and other cutting-edge technologies. If you got any questions or suggestions, drop them in the comments below. We would love to hear from you. Thanks for watching and see you in the next video. Take care. Adios.